in a way that was fully satisfactory to me. And so what I did was to start thinking about ways in which I could focus my work in a way that would answer that question. And so this talk today is really an attempt by me to show how I've tried to answer that question in different ways. And so after some time in reflection, what I did was to interact with a number of people, many of them from backgrounds that inspired me. And we identified problems that motivated group activities. And so one of these was the issue of how do you detect and treat cancer or disease in general. And this was a problem at the time because, of course, about 20% of death is caused by cancer. A lot of the challenges are associated with how do you detect cancer and how do you treat it. And this particularly inspired me because there were members of my family that developed cancer. And during that period, I would ask myself, what could I do with the knowledge of materials in a way that would be helpful to folks? We also became interested in problems of water purification. I started thinking about membranes for water purification and how to develop those with the approaches of materials. And how do you develop the next generation of solar cells and light emitting devices for people in remote places in ways that are enhanced by the science we can do in universities? And then lastly, how do you develop sustainable building materials? Now, in each of these areas, what we've done is to team up with collaborators. And since about 2000, we've had visiting faculties, graduate students, mostly from Africa, some from Latin America, come to our lab and work with mostly US-based graduate students and postdocs. And the work I'm going to show you today is a combined outcome of the collaborations between all of those that I've identified. So here are some of the visiting scientists from Africa. They range from the one on the top left who came to finish a PhD and is now the head of materials department at one of the leading universities in Africa, to people who started working on solar cells and LEDs and batteries in ways that are now giving rise to the results that I'll present in this talk. It also resulted in me recognizing that when folks very often would go back from our lab to Africa, they didn't necessarily have an environment where they could do research with all the appropriate supports. And so in a collaboration with the World Bank and the government of Nigeria, we were able to establish the African University of Science and Technology in Abuja, which is a university that focuses on preparing the sort of future professors in Africa. And over the last 20 years or so, this has grown from a concept to a reality. And it's a university that I was privileged to serve for 4 years in the sort of era between 2011 and 2014. Now, I'm going to start with the challenge of cancer and just talk a little bit about the two big challenges. So one is the challenge of early detection. If we could detect the cancer early, then of course we have more opportunity to treat the cancer. And then the other challenge, of course, is that the current treatment strategies are harsh because essentially about 1% or so or less of the injected drugs in chemotherapy reach the desired locations. So if one puts this problem this way, then the question is, how do you do early detection? And then the second question is, how do you do localized treatment to reduce the side effects of the cancer drugs that are often used to treat the patients? Now, one of the approaches to this is to take a basic approach that says, what are the mechanical ways that we might be able to use to transduce the presence of the cancer? So there are lots of probes in toolboxes that could deform cells in different ways, using micro tweezers, using optical tweezers, or traction force microscopy. And the methods that we chose to use were microfluidic approaches in which we could shear cells. And from the knowledge of the cell properties that we get when we shear these cells until they detach, we could then extract properties that could serve as mechanical biomarkers for the detection of cells. I'm going to talk a little bit about those. Then we could also, of course, use very specific adhesive interactions to also transduce the presence of receptors that are overexpressed on cancer cells. And so just to give you an example, I want to start with this video here of a shear assay experiment where we essentially flow liquid over cells that are distributed in a fluidic channel. So although you can't see it, the cells are being displaced. And gradually, as we increase the shear stress by increasing the velocity, you will see that the cells start getting deformed. And in this case also, you see that the shells start getting detached. So from experiments like this, what one can then do is by doing displacement mapping using digital image correlation, you can actually see how we start shearing the cells and inducing strains that are both tensile and but they are both axial tensile and axial compressive. And so with these kind of strain distributions, it's not surprising that as you increase your loading of the cells, you deform them more. And if you look actually to the top left, you'll see evidence in some cases of micro-buckling in segments where you have local compressive strains, and then axial deformation in regions where you don't. And so using methods like this, one can now start studying the cell as a material and treating the detachment of cells as an interfacial fracture problem. And so from these kinds of studies, you notice, for example, that cancerous cells basically deform much quicker, and the increase in the strain is much greater than those of normal cells, which are shown to the left. Now, as you detach the cells, what actually happens is you start peeling off the cell, and you now have a situation where you have these unfractured protein structures that are residues of the actin cytoskeletal structure and the vinculin. And so when you peel to a critical displacement, the cell flips off, as you saw in that movie, and then leaving behind on the substrate traces of the proteins that were in contact with the extracellular matrix. So what this basically shows from these traces of actin, which is present within the cell, is that these actin cytoskeletal structures essentially bridge the opening cracks in ways that toughen that process, in ways that affect then what the ultimate fracture energies become. So one can now use this information to model the contributions of these bridging filaments to the opening process. So one can take all this and now turn these into models that essentially idealize the opening and the shear deformation of the cells in finite elements. One can also introduce cohesive zone elements to really model the opening and cracking process that is associated with the detachment process. And similarly, one can do cohesive zone models where you use measurements of the true adhesion energies to determine the cohesive zone parameters. And so out of these kind of models then come experimental values of the critical energy release rate that are much greater than the theoretical values just associated with the cohesive tractions. And of course, the reason for the difference is because of the shielding contributions from the bridging protein structures. And the key result here is to say that the detachment of cancer cells gives rise to different interfacial fracture energies from those of normal cells. Now we can go one step further by looking at the shear deformation of the cells. And if you look at the flow of the fluid over the cells, what you find, of course, is that you induce local displacements due to creep deformation phenomena that are associated with the applied shear stresses. So using digital image correlation, one can now map the displacements, and from the displacements, you can map the strains as a function of time. And so this is from the work of Jingji when she was a PhD student. You see then that you go from a primary creep to a secondary creep regime, and then to a tertiary creep regime. And so from experiments, we were able to show that the cells undergo this kind of classical creep behavior. And you can get this information both in the nucleus and in the cytoplasm. And so in that way, you can now begin to fit the creep data to spring dashpot models that characterize the creep deformation of normal cells, as well as cancerous cells. So when you look at then the elastic properties, so the Young's moduli, for cells at different stages of metastasis, what you find is that the initial cells, which are non-tumorigenic cells, have high modulus. But as you go to the less metastatic cells, your modulus ranges reduce. And then as you go to the highly metastatic cells, you get even lower moduli. So basically the moduli reduce with increasing metastasis of the cells. And the same is true for the viscosities. The viscosity is also reduced as the cells become more metastatic. So what this basically shows then is that the moduli and the viscosities can be used as mechanical biomarkers of the progression of the tumor from no tumor to less metastatic to more metastatic. And what's going on, of course, is within the materials, in the normal breast cells, you have highly developed actin cytoskeletal structures that enable you to have relatively high modular structures. In the less metastatic cells, the actin structures are less developed. And in the highly metastatic cells, you get even lower density of actin cytoskeletal structures. And those translate into lower effective moduli and viscosities of these systems. And so if one goes back then to the sort of tensegrity model, one can begin to try to understand then the stiffness and the viscosity combinations that give rise to viscoelastic properties in terms of the development of the cytoskeletal structures, which seems to be less so as you go to less metastatic cases, more metastatic cases. The important thing here is, as you go to those late stages, if the cells are less viscous and less stiff, they can basically squeeze their way into different regions to induce metastasis in the body. The other important thing is we can now use these viscoelastic properties as mechanical biomarkers for the detection of breast cancer, as in the case of this study. Now, how do you prove this? So to prove this, we entered into a collaboration with the National Hospital in Abuja, and the National Hospital in Abuja gave us then access to 150 human breast tissues with triple negative breast cancer, which is the most prevalent form of breast cancer in that region, as well as breast tissue from people without breast cancer. And so in this collaboration, we were able to then look at the structure of the breast tissues at the different grades of tumor development. So the normal breast tissues look like the top left. You see well-developed cell structures in the top left image. In the early stages of cancer, you begin to break down those structures. By the time you get to grade 2, the structures are further broken down. And by the time you get to grade 3, the structures are further broken down still. So these can be looked at with different methods. We've looked at them with AFM techniques and light microscopy techniques that show that the morphologies of these structures change with grade. And you can also do indentation creep on those regions. And when you do indentation creep on those regions, you find out that the fastest rates for creep rates occur for grade 3 cancers. These are followed by grade 2 cancers in blue, and then grade 1 cancers in red, and then grade 0 normal tissue here in black. And so if you now extract for these the viscoelastic parameters for those different types of tissue, what you basically find is that the viscosity is highest for the normal tissue, and then reduces with increasing progression of grade from grade 1 to grade 2 to grade 3. And similarly, the moduli also reduce significantly from normal tissue to grade 1 to grade 2 to grade 3. And so with these kinds of results, you can see also that the changes as you go from one grade to the other can be more than the range in the data. So again, giving us a little bit of confidence that these kinds of viscoelastic measurements can now be used to track the evolution of the viscoelastic properties as you go from no tumor to grade 1 to grade 2 to grade 3 breast cancer. And so when you look at the statistical distributions of the viscosities, it's interesting to see what you find. So for the normal breast tissue, you have essentially almost like a normal distribution of frequency count for the viscosity. As you go from grade 1 to grade 2 to grade 3, the distributions become skewed with the low viscosity tissue dominating the results. And so what you find then is that initially you have a statistical distribution that's almost normal, but as the tissues become softer, the viscosity and also the moduli reduce to very low values, and the nature of the distribution changes. So with this kind of an approach, we've shown that you can change the moduli of the tissue and the viscosity significantly. But you can also, of course, use the fact that these tissues have receptors as a way of targeting the cancer tissue. And so you can use those receptors to bind to nanoparticles or drugs that are targeted. And once you bind to those nanoparticles or drugs that are targeted, you can now use processes of receptor-mediated endocytosis to take the particles in to the cells in ways that can enable imaging. And if you take drugs into the cells, you can also use them to enable treatment. And so with that in mind, what we've done is to explore different approaches to take nanoparticles into cells and drugs into cells in ways that enable us then to target cancer cells very specifically. And then we use magnetic nanoparticles because then we can use those to enrich the MRI imaging of the cells in a way that gives rise to ways of detecting the cancers early. So we synthesized the nanoparticles chemically or biosynthetic, or using biosynthetic approaches. We then conjugate them to produce these conjugated nanoparticles that have typical sizes between 20 and 30 nanometers. And with these nanoparticles, we can now do cell-based experiments or animal-based experiments to explore the targeting. Now, one question is, why do these nanoparticles get attracted to the cells? And to study these, we've done adhesion studies where we coat the tip of the AFM with the peptide or protein that we're trying to study as a molecular recognition unit. And we check to see what the adhesive interactions are between the tip and the cells. And so when you do this, you do a force microscopy experiment where you bring the tip in contact with the tissue, it jumps to contact. You then deform it up to some level elastically, and you retract down to 0 force, but the tip doesn't detach at 0 force because of adhesive forces. So what that means is you have to load it in the other direction until the tip detaches. The pull-off force is then the adhesion force associated with this situation. So with experiments like this, and these have been repeated multiple times, one can now measure the adhesion associated with luteinizing hormone, releasing hormone peptide-coated tips, and show that these adhesive forces are much greater than those that you get in the absence for normal cells. So this gives us a sense that this works at the cellular level. The reason it works at the cellular level is because you have overexpressed receptors, which are these LHRH receptors in green. And these overexpressed receptors are overexpressed by a factor of 4 to 5 or 6 compared to those in normal breast cells. Now, if you now look at breast cancer tissues at different stages of development induced in mouse models, what you find again is that the overall adhesion increases with adhesion stage. And that increase in the overall adhesion is associated with the overexpression of these LHRH receptors at those later stages of the tumor development. And you can go one step further to actually look at the adhesion in human breast tissue. And when you look at the adhesion in human breast tissues, what you find is quite interesting. So the first is you see from the AFM scans of the surfaces that these surfaces evolve as you go from grade 0 to grade 1 to grade 2 to grade 3 with a depletion, with some regions where you have depletion of material compared to others. And as you look at the adhesion forces, as you go from grade 1 to grade 2 to grade 3, you also see that the adhesion forces increase significantly as you go from grade 1 to grade 2 to grade 3. And so what that basically tells us is that the adhesion forces can be used as biomarkers for the classification of these tumors over and above the other methods that are used currently. Now, to begin to understand this, we've done molecular dynamic simulations here, working collaboratively with Nima Rabba, who is a professor at WPI, and his student, Avan Navabi. And what we basically have shown is that the adhesive interactions are associated with electrostatic interactions and van der Waals interactions with relatively small contributions from hydrogen bonds. And these adhesive interactions explain the specific nature of the interactions between the LHRH and the breast cancer cells. Now, this has major implications because it means, of course, that we can use these specific interactions to enable specific targeting. And we can also use a combination of these LHRH and PEG to really enrich the entry of the nanoparticles into cancer cells. But ultimately, with the methods that we have, this can become a method that's used for analyzing biopsies and perhaps developing coatings of functional groups for cell targeting. Now, in thinking about how the nanoparticles go into the cells, we've done some in vitro experiments and in vivo experiments to understand the processes. And what we find is that when the nanoparticles interact with the cells, You have clusters that form due to particle coagulation and adhesion, the disturbance of the cell membrane that enables you to have elastic bending of the membrane, and then the encapsulation of these particles and their transport into the cytoplasm, and in some cases, possibly into the nucleus. So if one were not thinking biology, one might think perhaps thermodynamics and kinetics. And so what I'd like to do today is just walk you through what the thermodynamics of this process looks like and what the kinetics of this process looks like, and how that might help us develop better drugs and better nanoparticles. And so in the case of the membrane, we have the energy of the receptor ligand per bond. We also have the elastic bending of the membrane, and we have the configurational entropy of the receptors that recoil as they attract the particles in. And so if one thinks about each of these energy components, then you can add the contributions from each of these to get the overall energy for free energy change for the entry of one particle into the membrane. And this is shown here. Well, one can also do the same for a cluster. In that case, you have to think about the free energy change of the nanoparticle interaction, nanoparticle medium interaction, and nanoparticle cell membrane interaction. And if one adds all of this together, you can get the total energy change for the entry of a cluster. And so with this, you can now determine the minimum size of a cluster that can enter to be about 14 nanometers, and the maximum size to be about 910 nanometers, which is consistent with experiments. And then one can think about the kinetics of the wrapping time as you encapsulate the nanoparticles, and think about the diffusion of the receptors into the encapsulation process. So if you do this for a normal cell and a cancer cell with different receptor densities, again, you find out that typical wrapping times can change from 81 seconds for the normal cells to 4 seconds for the cancerous cells. So with insights like this, you now can recognize that you can discriminate between the normal cells and the cancer cells by understanding the thermodynamics and the kinetics. And the optimum size for nanoparticle entry into the cells arises from the interplay between kinetics and thermodynamics. The wrapping times for small particles is thermodynamically costly and hence slow due to the sort of rapid increase in elastic bending energy. And then the wrapping of large particles is energetically more favorable, but slow due to the diffusive nature of the receptor transport. And so these kinds of insights are actually consistent with our observations in both in vivo and in vitro experiments. And they provide the basis for developing drugs and for doing imaging, as I will show in the next section. So let's look at the in vivo experiments more carefully. And in this case, we're going to induce a human version of the breast cancer by injecting human cancer cells into the mouse intravenously. These go into the mouse and they induce the breast cancer at the accelerated life rate of the mouse. You can also inject them subcutaneously. And when you do that, you can induce a xenograft tumor in the desired location in the mouse. And then at that point, you let that tumor develop, usually for between 14, 21, and 28 days. And then you can inject nanoparticles into the mouse to enrich the MRI images, or you inject drugs to shrink the tumor. So here's some results for the injection of nanoparticles. What you see is that when the nanoparticles are conjugated to LHRH, you get a darkening of the tumor in T2 contrast, which enables you to image the tumors at an early stage. The resolution we see here will enable us to do submillimeter imaging in ways that contribute to clinical cancer detection. We've also done work more recently using nanorods instead of particles of magnetite. And what you see is, again, after the injection of the nanorods, you darken the tumors compared to before in ways that help to discriminate for targeted conjugated nanorods, the presence of the tumor. So in the end, where we're hoping to get to is a situation where we will be able to detect tumors such as this in the breast through the interactions of nanoparticles or nanorods that are targeted to receptors that are overexpressed in the breast, that dock due to increased adhesion in ways that enable us to darken tumors in MRI contrast in ways that enable early stage detection. And then beyond that, we've used the same ideas to develop targeted drugs. And so you can induce the tumors at the early, mid, or late stages. And you can take cancer drugs that are targeted to the LHRH receptors and design them. And you can also test these cancer drugs by looking at their adhesive interactions with tumors at the early, mid, and late stage. And what you basically show is that those adhesive interactions increase with the stage of the tumor. And so with this kind of an approach, you can now take those targeted drugs, in this case, paclitaxel and prodigozine, and bind them to LHRH to see if you improve their efficacy. So here are some of the results that we've gotten. If you look at these results, in the absence of a drug, the tumors would just grow, which is shown to the top. But if I now take a conjugated drug, such as prodigozine or LHRH, what you see is the prodigozine with the LHRH shrinks and is eliminated within 8 days. And then the paclitaxel and the LHRH also shrinks and is eliminated in 8 days. So the two targeted drugs that we have enable the localized delivery of the drugs, and they shrink and eliminate the tumors without inducing significant cytotoxic effect. So for this part of the study, I hope you've been able to see that force microscopy measurements of adhesion can be used as mechanical biomarkers of triple-negative breast cancer cells and tissues. And the Shear assay and nanoindentation measurements of cell viscoelasticity can also be used as mechanical biomarkers. And these are important because they enable us to infer properties that can be used to characterize the different stages of progression of tumors in ways that can be translated to practice. And then we've also shown that the T2 MRI images are very much enabling in our ability to detect submillimeter tumors, which are really clinically relevant in ways that can save lives. And then lastly is these targeted drugs with LHRH molecular recognition units. Again, using the understanding of adhesion and specific targeting, enable us to shrink and enable tumors with much lower concentrations of drug. And so from this kind of a materials approach, blended with some mechanics, I hope that you can see the value of how we use these kinds of approaches, not just to develop lab-based modules, but modules that can translate to practice. So I want to change gear now and talk a little bit about some of the challenges of climate change and how they motivate our own kind of energy research. And of course, we're motivated to look at renewable energy because of the need to think about alternatives to reduce the effects of CO2 damage to the atmosphere. The other side of this, though, is that if you look at solar energy in particular, a lot of the people that need solar energy have limited income. And in many villages in Africa and even towns, people live on less than $1 or $2 a day. And a lot of those people lack electricity. And so if you look at the map of the world at night, you see that many places in North America, Europe, and Asia have electricity. Many places in Africa and perhaps some parts of Latin America do not. Those same places during the day show the converse, right? A lot of the places that don't have electricity at night have solar energy during the day. And so we call this the map of possibilities. And so the question is, what do you do about this? So within our group, we've been working on different kinds of approaches to harnessing energy, creating light, and storing energy. Again, guided by some simple ideas in mechanics and materials. And my first adventure into this was in a collaboration with Steve Forrest, who's one of the pioneers in LED detection. And Steve was trying to make some LEDs from stamping. An LED is basically a solar cell in reverse that basically takes incident charges and converts those into light with different wavelengths. And so by doing this, you can create light of different colors. And you can do this at different size scales. And so if I do this at the sort of micron scale, I can make pixels on a TV screen or a phone screen. And what Steve was working on in the early 2000s when I went to Princeton was ways of stamping those pixels onto these screens. And so we worked together on a mechanics model of the stamp. And the idea was to stamp the electrodes on to the LED structure in a way that was then something that could be automated once it was well understood. But they found that when they applied too much pressure to the stamps, the screens were damaged. And when they applied too little pressure to the stamps, then you didn't have adequate adhesion. And so what we did was to try to understand this. And we imagined in the early days that there are defects, impurities between the stamp and the substrate. So the nature of the contact is affected by the presence of these defects. What you have to do is to model the contacts as the stamps fold around the defects and look at what is the nature of those contacts and the sinking due to the defects in a way that allows us to optimize the process. The outcome of all this was a patent, and that patent, which was issued in 2011, is the patent for the OLED screen processing methods. And I have to say, it came from a collaboration with Steve, with whom I shared an office when I first went to Princeton. And so it's been licensed by Samsung, and it's a patent that's been generating some income for the last few years. Now, if you take an LED and you operate an LED in reverse, you make a solar cell. So we've made perovskite LEDs, and we're now making perovskite solar cells. And I'm going to talk to you about these perovskite solar cells in which you have these absorber layers that have these excellent absorption characteristics for sunlight. And by essentially applying pressure to these structures, what you can do is you can increase the contacts at the interfaces in ways that enable you to significantly improve the efficiencies of these perovskite solar cells. So we've been able to make perovskite solar cells with efficiencies of about 23.4% compared to the world record of 25.1%. So what interests me in these systems is that as you apply pressure to these systems, you close microvoids in these structures, and you increase the contacts of asperities in ways that enable more favorable pathways for the flow of charges to the electrodes. And so as we increase our pressure from 3 to 5 to 7 MPa, what you find is you reduce your microvoids, you enable more contact pathways. But when you go to 10 MPa pressure, you increase your microvoids because you start cracking the material. And so one can model these contacts and pressure effects. And at the end of the day, you can show that you start closing cracks in ways that affect or enable interfacial contact. And as you enable more interfacial contact, you have more charge transport, which basically improves the characteristics of the solar cells. And so this is why, as we've increased the pressures up to 7 MPa, your efficiencies have increased. But above 7 MPa, you start inducing cracks, which also degrade the power conversion efficiencies of these systems. So by blending mechanics and materials with solar cell development, we're able to actually create structures with world-leading properties. Now, what also happens is that as you apply the pressures, you also have some stress-induced amorphization around the interfaces. And that stress-induced amorphization is part of the story of what is going on as we apply pressure. And more recently, we've been able to show that as we apply pressure and we close up the pores and voids, you increase the lifetimes, the stable lifetimes of the solar cells in ways that suggest that further understanding of the transport phenomena associated with these structures could enable us to develop more stable perovskite solar cells in the future. Now, where we are now is we're taking a lot of this understanding, blending with machine learning methods to optimize the processing conditions with a spray deposition system for the fabrication of solar cells. And our goal ultimately is to enable the scaling of this research in a way that will allow us to take what we've done in the lab and scale it up to the possibility of making modules with attractive efficiencies and stability. Now, we're also doing similar work with batteries. A lot of the thinking is the same in that you can take the lithium-ion batteries. In this case, we're working with solid-state electrolyte that are less flammable and that have controlled porosity that you can use to store charges and ions. And essentially, by applying pressure to improve the contacts, what you can show is that you can enable the improvement of overall ionic conductivities and electrochemical storage capabilities. Now, as before, if you now do the strain mapping, which we've done with digital image correlation, as you increase the pressures, you get initially uniform strain distributions across the different regions. But when you get to higher pressures, about 1 MPa, you start inducing cracking, which degrades the ionic conductivities of these systems. And so with methods like this, we're now developing lithium-ion batteries with pressure-assisted fabrication processes in ways that are translating to interesting systems for further studies. Now, before I finish, I just want to answer the question that my mother asked me, which is, what difference does this make to the lives of people? Here I'm showing you a project that we've done in the Laikipia district of Kenya, where we introduce solar lanterns with LED bulbs and 6-volt batteries that are the same as motorcycle batteries. With those simple systems, we're able to provide about 10 hours of light at night to communities in this rural district in the Laikipia district of Kenya, which is about twice the size of the country Israel. Or you can charge a cell phone, or you can power a radio in a rural community. In the early stages of the project, I wasn't sure whether or not this was good enough, but I hope you can see from the faces of the people what difference this has made to this community of 200 homes in a way that is truly transformational. By the way, what's even better about this is the people paid for these solar lanterns with their energy budget, which is what they used previously to buy kerosene. Today, they no longer consume kerosene, and so they have discretionary funds that they can use for other things. But because they're no longer consuming kerosene, their kids don't have asthma and pulmonary diseases that were a major challenge in this community. We've also used these flexible solar panels here in transporting medications and vaccines to many, many stations in that Laikipia district in ways that are enabled by the applications of these technologies that are changing lives and helping lives of rural people across many villages in that community. So I hope that this talk has given us some examples of the applications of materials for health, energy, and the environment, and that you can see some of the opportunities to develop, for example, mechanical biomarkers and targeted nanoparticles and drugs using basic ideas in our understanding of adhesion, contact mechanics, and using those ideas in ways that can translate to practice. I also hope you see the opportunities, for example, in using our knowledge of mechanics to design contacts that enable material transfer and also the control of performance of LEDs and solar cells in ways that create devices with the opportunity to translate. In all of these examples, though, what I've learned from doing this kind of work is that as we do this kind of work, it's important not just to think about the research, but to really think about how this research and the outcomes enables people to use these kinds of outcomes in science, technology, and innovation as tools for their own self-advancement. Thanks for your attention. I'll be happy to answer any questions that you have. Thank you.
Okay, thank you, Wole, for the great talk. I myself are also learning a lot and find it very inspiring. So let's now open the floor to the audience. So if you want to just unmute yourself and ask directly, okay.
Hey, good morning, Professor. Oh, Shadow, you go ahead.
No, you please go ahead.
Good morning, Professor Soboyejo. This is Xiaoning Jian here. Thank you for this interesting, quite a few interesting topics. My question for you is about the adhesion force-based, using that as a biomarker for cancer early diagnosis. So I saw very impressive in vitro and ex vivo results. I'm not sure about the in vivo translation. Do you think that's something we can see in the near future, or that's already in the clinical trials or in clinical practice?
You raise a very good point. I think the initial experiments we've done are very promising. And in fact, I'm amazed by the consistency of the results. What we need to do now is further refinement of the in vivo studies in humans in ways that I think will establish this. I think so far, everything I've seen basically points to further validation of what is already a reasonable initial population. And so I expect this to be one of the things that can translate to practice in relatively short period of time, building on this kind of approach.
Great. Thank you.
Young.
Hey, Wole. Very nice talk. I think you highlighted a few examples where mechanics and materials can play an important role. You briefly talked about cold welding. I understand between the two metals, especially in the small scale, cold welding can happen. Can you elaborate a little bit more, let's say, in the process on the water conditions, on the water pressure, or maybe also time dependent? Yeah, can you?
Yeah. So this is an interesting question. So the first question is, what happens during cold welding? okay?
Right.
And so if you have really clean gold surfaces or clean silver surfaces, and you bring them into contact, you know, what Steve Forrest taught is you get electron overlap, and that leads to welding, right? Now, under those conditions, you need very modest contact times, right? For this kind of process to happen. But what also is important to realize is that you can get hydrated oxide layers present even on gold surfaces and silver surfaces. And you can also get impurities present associated with your clean room environment. And so if you look at the results we published, you will see that what those enable are sort of contacts that occur over the obstacles, right? And those will then determine the contact lengths associated with the different pressures. But generally the pressures are low comparatively. And then the contacts depend on the stiffness of the contact plates. And so the important thing there is to use more compliant stamps, because those increase the effective contact for a given pressure. So generally the times can be very short, a few seconds. They don't have to be prolonged. What's more important is the compliance of the stamp, and then trying to minimize to the extent that you can.
So your stamp is a soft material, right? Like a PDMS.
Yes.
But you have a metal coating on top of the stamp, and then you have another metal on the substrate. So this the metal contact.
Yes.
Okay. But yeah, okay. I guess the coating layer is very thin on top of the PDMS, right? So the PDMS.
Yes, it is.
Would matter. Okay. Yeah, that's a very interesting phenomenon. Okay. Thank you.
Thanks, Jan.
Hey, Wole, thank you for the wonderful talk. I do have a questions regarding to the fundamental analysis for your cancer cell that at the crack front. I see that the deformation of the cells actually is substrate dependent. So you do a fundamental ABAQUS simulation, and then you use like several different spring, and then to simulate it, and then to get the energy, release rate. Have you do any follow-up study to see if different, substrate or different cancer cell with different spring constants for the spring at the crack front? Did you do that? And then to explore a little bit about the, the different deformation?
This is a really good question. So one of the things that I needed to point out is that on top of the substrate is a layer of extracellular matrix. And then on top of the extracellular matrix is the cell itself, which is then attached through the focal adhesions to the extracellular matrix. And then underneath that, of course, is the substrate material. So what we've done is we've done finite element simulations in which we incorporate the properties of each of those layers, including the substrate, into the simulations. But the springs that I showed are springs between the cell membrane and the ECM.
Mm-hmm.
So generally speaking, those springs calibrate that detachment, and the substrate effects are not as significant under those conditions as one might imagine. But in the simulations, we incorporate the elastic or whatever properties of the discrete layers. We've gone through the challenge of measuring all those properties in different experiments, and then we incorporate them into the simulations to determine the different parameters.
Okay, thank you.
You're welcome.
Okay, so thank you everyone for the question. I know there might be more discussions, but in lieu of the time and the upcoming meetings, let's thank Professor Soboyejo again. And I appreciate your time today and hope you enjoy the talk.
Thank you.
Thank you. Thank you very much. It's been nice meeting everyone. Thanks for your time.
Okay. So Shelby and Wally, I will put you into a separate room. So if you want to join that, so we can start.
Sure.
Okay. Thank you.
I will see you both later.
Yeah,
Great.
see you.